Hello everyone, my name is Joshua, who is in charge of the technical service of IDC, Industrial Device Connectivity. Today, I'm going to introduce the product of MB3000 Series. For the lesson, it is talking about the function of IEG MB3000 Series with IEG Manager. So, in the lesson, you will learn how to configure in IEG Manager and how to use IEG Manager for troubleshooting. This is my agenda. I will first go over the mobile gateway solution for MB3000 series. Then, we will jump into configuring the IEG with IEG Manager. And the last part, I will teach you how to troubleshoot by using IEG Manager. Now, let's start from mobile gateway solutions. The first and second are the original usage, a mobile's RTU master to a mobile's RTU slave, and mobile's TCP master to a mobile's TCP slave. The third one is a mobile's RTU master communicates to a mobile's TCP slave. The fourth solution is mobile's TCP master connects to a mobile's RTU slave. But there's a limitation of the first solution, the distance. If there is a mobile's RTU master in this building, for example, the central control room, how could it communicate to a mobile's RTU slave in another building far away? No worried, IEG provides an advanced solution to overcome the limitation, PROCOM function. If the mobile's RTU master is in Windows space, it can install our PROCOM driver to let the mobile's RTU packets to be sent out on the Ethernet. It provides two more solutions. Solution 5 is a RTU master connects to a mobile's RTU slave through PROCOM on Ethernet. Solution 6 is the RTU master communicate to a TCP slave on Ethernet directly. After introducing IEG solutions, I believe you have already excited about the solutions and strongly wish to learn the way of the IEG usage. In order to configure the MOSA IEG MB3000 series device, a utility called IEG Manager must be used. The image on the slide displays the main screen of the IEG Manager. If you would like to know the version of the IEG Manager you are currently running, click on the icon on the left top hand corner of the window. In the page, it shows you the function of offline configuration. You can use it for two purposes. First one, create new configuration. For example, if you don't have IEG by hand, but you would like to configure it in advance, you can use it to produce a configure file. After you get the IEG, you can import the configure file without setting. The second one, load existing configuration. The function is usually used for troubleshooting. If customer provide a configure file, but you don't have IEG by hand, you can use the function to load the file to see the configure setting. The IEG was designed with the ease of use in mind. For basic settings, it takes 5 steps to configure your IEG MB3000 series. The first step is the mode tab. The mode tab is where each serial port operation mode is configured. The operating mode determines whether the devices that are connected to the serial port will operate as a master or a slave, and whether the mobile's RTU or mobile's ASCII protocol will be used. To select the proper mode depends on your device. If your serial device is a slave, then the IEG should be in slave mode. If your serial device is a master, then the IEG should be in master mode. Make sure to select the proper mode for the protocol you will be using. The advanced IEG MB3000 series supports the serial redirector function. The serial redirector function can be used as a Modbus serial protocol converter, or simply just allows the Modbus serial master to pull a Modbus serial slave. On the slide demonstrates a ASCII to RTU protocol conversion. Next, in the Network tab is where you can set the network configuration of the M gate. In the Serial tab is where you can set the serial configuration of the M gate. Moving on to how slave IDs are mapped on the IEG MB3000 series. When a Modbus master requests information from a Modbus slave, the request is addressed to the desired slave's ID, which must be unique on the network. If this is not properly addressed, a request sent to the slave ID will receive more than one response, causing communication error. Basically, the slave ID map is where you define the slave IDs or IP addresses, depending on the mode you are using. For the slaves, they are connected to the serial port or Ethernet port. I will explain the ID shift and smart routing and remote TCP slave ID in the next few slides. ID shift. The legacy Modbus serial slave may have the same unconfigurable ID. The way to communicate to those slaves is to shift their IDs to be different from each other when talking to the master. So, you need to understand the relationship between master and slave and use the spatial offset field. Let's look at my formula. The real slave ID equals virtual slave plus offset. When ID equals 4 is coming from TCP master and passed to serial device, MGate will shift the ID according to value of offset, and the ID will be shifted to 7. Of course, when response message sent back to master, the ID will shift back ID 4. Routing. The routing concept is designed for the multiple MGates like the 2 and 4 port models. When multiple slave devices that have the unique slave IDs connect to the serial ports of the multiple MGate, the MGate will need a way to send the request from the master out the correct serial port. The solution would be to define the slave IDs that are connected to the serial ports in the slave ID map. This slide displays the MGate in master mode. In order for the request to reach the appropriate slave, you must add the IP addresses of the remote TCP slave in the slave ID map. In the case, 3 channels will be defined. This slide introduces the multi-master and multi-request supports of the MGate. When the MGate is set to slave mode, the MGate will support up to 16 masters connected to the MGate simultaneously. We designed a mechanism that can handle a maximum of 512 queues without dropping them. This means that 16 masters could send 32 requests each at the same time. Moving on to the 5th tab, the Modbus tab. The Modbus tab is where certain adjustments can be made to fine-tune the communication between different Modbus networks. You can configure initial delay, Modbus TCP exception, slave channel, and response timeout. An initial delay may be required when using certain Modbus devices that take longer to boot. You may set the amount of time the MGate waits before sending the first request to the slaves. Furthermore, a Modbus TCP master might require a TCP exception to be sent when an error has occurred on the serial side. Simply enable Modbus TCP exception. The Modbus tab also contains the response timeout setting, and Modbus auto detection feature can be used to automatically detect the best response timeout value for your communication to your slave devices. The auto detection function works by sending a request to the slave device with function code 08 diagnostics. The MGate will then calculate the timing the MGate needs. Above are the mobile's basic concepts. Next topic will be the PROCOM function, and we will talk more details about it. Let's talk about what is PROCOM. PROCOM can provide a virtual COM port on the Windows base that mobile's RTU master to keep all the same settings as before. For example, through the SCADA software on the mobile's RTU master, it is still sending the port link through a COM port. Through this COM port is on the Ethernet, so it can extend the distance limitation of the serial interface. It can connect to anywhere, everywhere. PROCOM supports by advanced IEG MB3000 Series. Firmware version should be version 2.0 and later. MGate Manager version should be version 1.4 and later. This is a convenient function and also easy to configure. There are only 3 steps to set it up. Step 1. PROCOM mapping. Step 2. PROCOM enable. Step 3. Slave ID map. This is driver's line, PROCOM mapping. This is firmware's line, PROCOM enable. Most applications should configure as RTU master or ASCII master. It means the SCADA request to the slaves. Let's configure port 2 as a RTU master mode as an example, and see how do we set the slave ID map of next slide. The port 2, first PROCOM, is configured as mobile's master mode. There is no slave of the channel, so we cannot see the port 2 at this step. In contrast, we can see a mobile's TCP device at an IP and TCP port by channel 6 as a TCP slave. Through port 3 to port 5, these PROCOMs are configured as a mobile slave mode, so we can configure a slave ID of it. Sometimes, the mobile's communication may go wrong, so we would like to share our experience with you about how to monitor mobile's traffic. Let's take a look at the example network topology. A mobile's TCP master connects to a mobile's RTU slave through our MGate MB3000. At first, everyone goes well, but the SCADA reports an exception or response timeout, or maybe lost the mobile's RTU slave. How do you know which part of the topology could be wrong and make this error happen? Our MGate MB3000 Series provide a monitor function for you to check the mobile's traffic, and you can know which part might be wrong. Here shows how to use the monitor function. Just click the start button. You can start to capture the mobile's traffic. In the next slide, I will introduce several typical behaviors you might see in a mobile's monitor log. The first one is the mobile's TCP master to a mobile's RTU slave. The first record is the TCP request from the TCP master. You can see the IP address and the TCP port. This is a TCP request at the type column. Then the slave ID, function code, and other detailed information. The second record is the RTU request, which the MG3000 series translates from the TCP request. The third one is getting from the RTU slave as a response. The last is a TCP response from MG MB3000 series to the TCP master. The second one is a mobile's RTU master to a mobile's TCP slave. The RTU request comes in from port 1 and MB3000 transfer it to a TCP slave on Ethernet. The TCP slave thinks MB3000 is a TCP master, so it responds the request to MB3000 and then MB3000 transfer it to port 1 to the RTU master. This slide shows an example of program. You can see on the monitor log we highlight it as a program packet, and in fact it is a RTU request from an Ethernet PC. And then the RTU request goes out on port 1. Get the response, then send the RTU response to the RTU master with program. The slide shows you what you will see if the slave device is a Modbus TCP slave, similar to the last slide, but only change the packet 2 and 3 to TCP request and response. Next will be two examples of abnormal behaviors. First one is the Modbus RTU slave doesn't respond the request. You can see that there is no third record as the RTU response. This may be caused by the RTU slave is power off or it cannot recognize the RTU request. Case 2 is exception. When RTU slave receives the request correctly but cannot handle it. For example, if the request is to read a non-existent output or register, the RTU slave will respond an exception response, just like I highlight on the slide. If the monitor log you have is not the case I introduced here, it might be too compressed to you. Don't worry, you don't have to analyze it. First click the stop button and save it, then contact Mozart support. We can analyze it and help you to fix your question. Sometimes, if the question is caused by the Ethernet side, the Wireshark log may also help. Thank you for your time, and this is my presentation. Thank you.